Lenz's law. We're going to take a look at where that negative sign in Faraday's law actually comes from. Lenz's law was actually developed after Faraday's law, but really when we write down Faraday's law of induction, we're using the work of Faraday and Henry plus the work that Lenz did a little bit later on. This is also important for the next chapter, chapter 14, where we talk about magnetic induction, or inductance, I should say. So, Lenz's law talks about what direction the EMF is going to set up. If you remember the right-hand rule, we know that if we have a wire of current, the magnetic field is going to wrap around it according to the right-hand rule. Likewise, if we have a magnetic field, to produce a magnetic field in a particular direction, using the right-hand rule again, the thumb will point in the direction, if the current's going around with your fingers, the thumb will point in the direction that the magnetic field goes. Okay, so let's take a look at this case. We have a conductive ring, copper maybe, and we have our bar magnet. Let us say that in this particular case, that we are moving this magnet toward this ring. Okay, so what's going to happen here is that the magnetic field is going to get greater and greater inside this ring, or I should say the magnetic flux is going to build to a larger and larger value as this magnet gets closer and closer. Lenz's law states that the direction of induced currents, okay, the currents are induced by the EMF from Faraday's law, is always so as to oppose the change which caused the current. Okay? So what change are we seeing? We're seeing a stronger magnetic field, magnetic flux inside this ring. Okay? So how can we oppose this increase? Well, to oppose the increase, we can create a magnetic field in the opposite direction. Using the right-hand rule, we know that if the field is changing in this direction, we want to create an opposition to that direction. So here's my right hand. This is the direction of the opposing or the induced magnetic field, and the current is going to go in this direction due to an EMF. Okay? So once again, there's two magnetic fields that are present here. We have the magnetic field from the applied, or the applied magnetic field from this bar magnet right here, and we have the induced magnetic field which is pointing in the opposite direction. Okay? So an increase in magnetic field, that is going to induce a current in this direction. If we pull the bar magnet away, as in this case right here, then we're going from a higher magnetic field to a lower magnetic field. We are still having a magnetic field in this direction, but the change is in this direction. So in order to sustain the same intensity of magnetic flux, okay, we want to have a magnetic field in this direction, so the current induced is going to go in the opposite direction. Okay? So this is Lenz's law, and this is that negative sign that we saw in Faraday's law, where we saw that the induced EMF was equal to negative N times d phi dt. Okay, the negative is this direction that the current is going to be induced that opposes any change. Okay? And again, it might seem a little counterintuitive at first, but when you think about it, many things in nature resist change. So why not, if we're inducing a current here, that induction be a result of any change? We try to slow the change down. Again, let's take a look at another example. Here we have a magnetic field which is applied to this ring right here. And then we suddenly take the magnetic field away. Well, what is going to happen inside that ring? Well, initially, the induced field for the sudden drop-off in the magnetic field is going to be just as strong as the original applied field. But slowly, as this current wraps around this ring, the magnetic field is going to decay as more and more the energy from the electrical current is dissipated due to resistance. So in this particular case right here, again, we apply some magnetic field, suddenly take the source of the magnetic field, the applied magnetic field away. The ring says, no, I don't want to change this too rapidly, so I'm going to induce a current in the ring to sustain a magnetic field in that direction. But we see it dies down pretty much exponentially because, again, this is due to the ohmic resistance of this ring right here. Okay? So again, you can't abruptly just make a magnetic field disappear. Okay? There is, in this particular case, an opposition to the sudden change in the magnetic field. And this results in the current that we produce. So again, thinking about increasing the magnetic flux through a particular ring that we may use to induce a current. Again, the change is in this direction, so we oppose that change, and the current will wrap around in this direction. If we flip the polarity right here, okay, the magnetic field is pointing this direction, all right, but again, we're changing, so we're going to oppose that. We're going off in the other direction right here. Now here's some applications of Faraday's law and Lenz's law. The electric guitar replaced the soundboard of the acoustic guitar with these pickup coils. And the pickup coils, basically through induction, can generate a signal which is then amplified. Now the acoustic guitar, we talked a little bit about string instruments, didn't spend very much time on them, but we understood that the standing waves on the strings would cause the string to vibrate back and forth. The vibrations would then be attached to the bridge. The bridge of the acoustic guitar would pull up and down on a soundboard. The acoustic guitar is hollow, so it acts like a Helmholtz resonator. It amplifies that sound. And really what happens is the energy from the vibrations of the string are transmitted or transferred to the soundboard. The soundboard does work on the air, and that converts the transverse waves on the string to acoustic waves that you hear. Now for the electric guitar, things are a little bit different here. We still have vibrating strings. We still have transverse waves traveling up and down on the string. But these strings are made out of steel. Steel is ferromagnetic. So anytime we have a ferromagnetic material inside a magnetic field, what's going to happen? The magnetic field line is going to concentrate in that ferromagnetic material. Okay. Now, this is our string right here. Again, it's going to vibrate back and forth. It's sitting right above these pickup coils, which are essentially permanent magnets. Okay? So as a string vibrates back and forth, it is going to disturb the magnetic field from these permanent magnets. It's going to change that. Well, here's Faraday's law of induction. If we wrap a coil, what we call a pickup coil, around this magnet, and the string vibrating above it is slightly changing the magnetic field. Okay, we're changing the magnetic flux through the pickup coil. That is going to induce a very small current, which can then be amplified. Okay? Originally, when the electric guitar came out, they'd use vacuum tubes to amplify the current. In fact, the use of vacuum tubes allowed them to actually distort the signal, and this led to a large number of effects that they could use with the electric guitar. Today, some people still use tube amps, but for the most part, we use transistors, and in fact, in some cases, they'll simply just digitize a signal and then use computers to add different effects here. But again, the energy from the vibrating transverse strings is converted into a very weak electrical signal, and that weak electrical signal can then be amplified and further processed. So there's one application. Another application is actually used in small infants who may have not developed enough in terms of their central nervous system and perhaps could be at risk of what's called SIDS, sudden infant death syndrome. In this particular case, the central nervous system is not developed to the point where if the child stops breathing, they're going to start breathing again. Unfortunately, this led to a few deaths many years ago. But now, with this technology, we can actually put a detector. Basically, all it is an induction loop. And what happens is, as a child breathes, it doesn't put very much force on them. They expand and contract the overall area of this, and that'll change the magnetic flux. So this breathing monitor can really detect whether or not the child is breathing. And simply what's happening is you get this very weak induced current, which is oscillating with respect to time as the child breathes. If the detector no longer detects this, an alarm will go off, and all that has to be done is the child is woken up, because as the name implies, this usually happens in their sleep. So again, very simple application of Faraday's law. It's called an apnea monitor, and again, it detects this problem, which all these children grow out of very quickly, but it can be a problem soon after birth. Sorry about that.